So let's see how to create our own high-pass filter. First, I'll show you how to define your own custom kernel, and later we'll use OpenCV functions to help us build commonly used filters. Here's an image of a building. It's actually San Francisco City Hall. I've read it in, and as usual, I've made an RGB copy for image processing. The first thing I'll do is to convert this to grayscale using CVT color and the code RGB to gray. This way, a filter will be able to detect changes in image intensity. Next, I'll create a custom edge detection filter. I want to build one that detects vertical edges and ignores horizontal edges. I'll do this by making a 3x3 matrix and using values that will calculate the difference between the left and right sides of this pixel area in an image. I'm starting with an empty 3x3 kernel. I'll put negative values on the left side, weighting the corners less than the edges right next to the center pixel. I'll put zeros in this center column, and then positive values on the right side. This kernel, once centered on an image pixel, will calculate the difference between pixels on the right side and the left, thereby detecting vertical edges. This is actually a really common filter called the Sobel filter. The Sobel filter detects abrupt intensity changes in the x and y directions separately. This one is an approximation of the gradient, or change in intensity over space, in the x direction. And I'll actually name it Sobel X. Then, to convolve this filter with the input image, I'll use an OpenCV function called filter2d. This function takes in an input image, the type of output image, a -1 just means the output will have the same type as the input image, and finally the kernel we just created, Sobel X. And it produces a filtered image. Let's display it and see what it looks like. And I see basically what I expected. All the vertical edges are highlighted. And this kind of filter helps me detect the vertical edges of the building and the structures that surround it. My last step, which is a useful thing to learn in computer vision, is turning this image into a binary image. That is, I want to turn this into a purely black and white image, with the strongest edges clearly visible. And to do that, I can use the OpenCV function threshold. This takes in our filtered image that we want to perform the threshold on, a low value for the pixel values to pass through, and I'll set this at a medium-high level at 100. Then it takes in the pixel value to turn these all into, which I'll set as white or 255, and finally the type of threshold, a binary threshold. And I'll display this image. Here we can see the stronger edges clearly. And if I lower this threshold to, say, 50, and run this code again, I'll detect more edges. In fact, too many edges to really be helpful. So let's go back to a 100 threshold. So here I am zooming in to see the difference between this first filtered image and this second binary image. We can see that in addition to the edges of the building and windows and other structures, there are a lot of other smaller detected edges, these dots on the grass for example. And these don't provide any extra information about the building or scenery. They're really just spotty noise. Noise is usually represented as dots or fuzzy details. By detecting edges like this, a high-pass filter can actually exaggerate noise in an image, so we have to be cautious when we apply these filters. Often, we have to take an additional step to make sure we don't enhance undesirable noise. Soon we'll see that we can use a low-pass filter to blur an image and reduce unwanted noise. We'll often do this before applying a high-pass filter like this, and we'll get into the applications of low-pass filters after you get a little more practice applying high-pass edge detection filters.